So today we have new material. Tuesday, we're not meeting face to face, so y'all are watching videos. So there is new material that day, but it's not a lecture day. Thursday is our review, right, for exam 2 next week. Ooh, I didn't bring printouts of the sample problems, but they're in D2L. Sorry, guys. I think I brought any. I'll look, but I don't think I did. But they are in D2L, so you can see the sample problems for next. It's next Tuesday, not Tuesday coming up, but the next Tuesday is our exam, November 24th. And that's it. That's all we're meeting. So your presentations are due next Friday, all that stuff. But this is our last meeting where we will be covering new material. Here's the overview of the semester. Yeah, I know it's ugly, but that's what I got, guys. So you have new material on D2L on Tuesday. You are not Zooming with me and you are not meeting with me on Tuesday, right? But if you have questions, you can email me and stuff like that. But other than that, this is our last little bit of new material as a group. It's awesome. We're almost done. So make sure that you're starting to think about thinking about exam number 2. I don't want it to come as a sudden, oh my gosh, there's an exam. Okay, it's in a week and a half. And we have the proof project due next Thursday, right? It's a week from today. Is that right?
The 19th, yes.
Yeah, due on the 19th. There it is. Top. Okay, so with that in mind, there will be proofs on the test too, of course. And I wanted to work one of the proofs out. Ashley was in my office the other day and she asked about it. I kind of played with it and played with it. I think I left a step out of the hint is what happened.
Okay.
I was like, we're not quite seeing what I want to see. And then whenever I went back, I was like, oh, yeah, this is what happened. So we're going to go over, which number is it?
7.
It's number 7 on the second page.
The angle bisector the triangle.
Is that 13.4 or 13.3?
688.
Okay.
13.3.
13.3. So that's like page 712 in the other book. So, which one you got? Okay, so and this was number 7. It says something along the lines of prove that all 3 angle bisectors in a triangle are concurrent. Something like that.
The angle bisectors of the sides of the triangle.
Angle bisectors. Well, they're of an angle, right? Of a triangle are concurrent. Okay. And I think that my hint was like, look at number 6 or something like that. She's like, it wasn't a very helpful hint. So we're going to do a little bit more than that together now. Okay. And I think that what we have to watch out for whenever we do proofs like this is try not to make, like when you do your picture, try not to make assumptions. So these are not equilateral triangles. They're not isosceles triangles. So try not to, we usually will draw a triangle that looks something like this, right? Which is pretty equilateral. But remember that we can't just assume these angles are all congruent. It's like you could draw your crazy triangle, right? Something more like that if you wanted to. Anything, it doesn't have to be a nice, pretty equilateral. So try not to make assumptions when you do this. I'm just going to do ABC. Okay. And I think that in number 6, I had said something like, draw your, that one was bisecting the sides, right? Okay, so I'd said bisect 2 sides and show that they meet in one point in the middle, okay? And we know that that's true because if I do any kind of a segment and they meet, they're going to meet in one point, right? We know that 2 lines meet in one point, okay? So I said, look at that, but apply it to angles, basically. So here I'm going to do angle bisectors. Okay. And they will meet in one point. I'm going to call it P. Okay. We know they meet because unless they're parallel, they will meet eventually, right? Okay. But what we have to watch out for here is if this is an angle bisector for angle B, then yes, I can mark this as congruent to this, right? These two smaller. Zoom in a little bit. I can make those two smaller angles congruent. Really? Okay. But what I can't do is make these two small angles congruent to these two over here. I can say, yeah, C is bisected also, but I have to give him like 2 hash marks, right? And so that's where I said, watch out, because if we draw it too equilateral-ish, then it looks like, oh, well, I can say this one's congruent to that one, but I can't. So if we drew more of a scalene type triangle, it would be more obvious that they're not necessarily congruent to one another. So watch out for that. Okay. So the piece that I did not, I should have given you an extra hint on 7. So use the stuff from number 6, but then what I should have said was something to the effect of construct a perpendicular from this point of intersection to all 3 sides. Okay, that's the little hint that I left out. So that's going to make things a lot easier for us. And people go, well, how would I know that? You don't until you've played with them a lot. And you're like I was playing with that one that Ashley and I were doing. And I was like, we're just missing a piece of information, basically. We need one more piece of information. And if I make this, let me do this a different color. If I make this perpendicular over here, now it doesn't have to be the perpendicular bisector, right? So be aware of that. We're just saying construct a perpendicular from this point where these two intersected to all 3 sides. Okay. Mm-hmm.
No. Will the line that bisects the angle create that perpendicular?
No, they're not. So that's a really good question. So we can't meld the proof from number 6 with the proof from number 7, because the one from number 6 was they have to be perpendicular bisectors, right? And on the sides, but this is not. These are just, the only thing that's coming up here is angle bisectors. Okay. So the only thing we know for sure is this guy is cut in half, this guy is cut in half. All right. But we do know we can construct a perpendicular line, right? So that's okay. You can always create a perpendicular line. So that's all I'm saying here is let's just make 3 perpendicular lines. And that's your little hint that I didn't put in, sorry. Okay. Once we have that, I think it'll fall in place. So we need points of intersection just so we can talk about them. You can call these whatever you want. How about, I don't know, D, E, and F. D on my left side, E on the right side, and F on the bottom. And I did say in the hint for 6, use some transitivity, which is what we're going to see that we've got some stuff that's congruent here, which is nice. Okay, so look at it like this. I have 2 little triangles that I've created over here. What do we know about those 2? So I'm talking about DPB and BFP, those 2 little triangles right there. When I look at that picture, I think to myself, gosh, it almost looks like a kite. You'll see it? It almost looks like a kite. So if we could show that it was a kite, we could see that those are congruent, right? Everything there would be congruent between those 2 triangles. So can I prove that is my question. And those 90-degree angles are what's going to help us. I'm sorry, I just didn't hear you.
Are we allowed to draw one from D to F to do the diagonal with this normally with the type thing where I would approve more of the angles?
That would give us smaller triangles and we don't need them, but you could if you wanted to. You can always throw in extra information. Reading off of Mary, she says side angle, angle. And I would say you're correct, except for one little problem. Right now, we can get there. My angle and my angle. Oh, which side are you after, Mary? I'm sorry. She could be okay. Same segment, right? That's what I'm hearing. I think that probably is what she was wanting.
Yeah, she said the side they share.
The side they share, absolutely. Okay, good. Let Alexis in. Okay, so we know that we've got an angle and then another angle and then a side that they share. Angle, this angle, and the side share. Absolutely, Mary. Great. Okay, so those two are congruent, which means that these two perpendiculars are congruent to each other. Does that make sense? Because they're corresponding parts on congruent triangles. Okay, so I'm going to put just one little hash mark on each of those. Is that okay? Okay, and then I want to use a similar thought process for these two more kind of elongated triangles over here. Same thing, right? Okay, so when we look at them, I'm going to double hash mark that middle guy. We look at them, we say, oh, it's that right angle that's helping me out. And that's what we were missing the other day. We've got angle, angle, and then the side that they share again. Okay. Okay. So since that's true, and this piece right here corresponds with this piece right here, those must be congruent to each other. Okay. And now we have this one's congruent to this one's congruent to that one. So I'm just going to put one hash mark on that extra piece over here. All right. And the kind of cool part of this is if I had done this as a scaling triangle like this, it wouldn't matter because when I make this perpendicular and I make this perpendicular, and this is an angle bisector, even with a really long drawn out triangle, it doesn't matter, they're still congruent. Question?
That point where they meet, like the top of the kite, is that just where the angle bisectors intersect?
Yeah, that was the intersection for this segment and this segment. And we just said, we know two segments make a point, right? Meet in one single point. We don't know that three segments have to meet in the same point. So that's why we can't assume that the third one is. Oh, be careful, Demondre. So I can't just drop down like yet, drop this down and say, oh, that's the third angle bisector, so and it meets concurrently, but we're going to show that it does. Okay, so far we know this one and this one meet because any two line segments can meet in one point, as long as they're not parallel, right? So that's how we got this P guy up here to begin with. It doesn't matter where that point is. Like I said, if it had come way out here, as long as they meet right there, we still would have kites, basically. It looks like kites to me whenever I look at those two triangles
I
together.
think the other thing is I kept looking at the three triangles with B, E, A, and then we're also looking at those triangles.
The bigger one, B,
And
E,
there's
A.
probably a way to prove it.
Yeah. Well, and with the 90-degree angle in there, we're probably better off to prove that, right? So, yeah. Eventually, we'll have all kinds of triangles congruent here.
I got confused because mine doesn't look like a kite, but I know where I went wrong.
Did you do the perpendicular?
I did. My angle bisectors just
Aren't really bisecting.
Yeah.
That's okay. My pictures never really look exactly right, but I put the little marks on them, then force it, right? It doesn't matter if it doesn't look that way. I'm telling you it is. So as long as you are notating it correctly, you'll be all right. Okay, So we have all of this concurrent or congruent. We have these little pieces congruent, and we have these two concurrent in one point. What we want to do is now we want to construct a line segment between A and P. Now, what we're not going to do is we're not going to say it's the angle bisector yet. Okay. We know we can construct a line segment, right? Any old line segment will do. And now we're going to look at these two triangles up here. The APD and the APE, those two triangles up there that we just created by just dropping a line segment. We didn't say anything specific about it. We just said basically it connects A to P. Okay. But now I have two more triangles, and they suspiciously again look kind of like a kite, right? So think about that. Do we have it?
Yes. Side. No. Side angle.
Okay, but what do we know about side angle?
Similar.
Oh, that's the bad guy, right? So we're close, but we want to make sure. So is everybody okay with this side they share? Okay, and we know that this angle has to be congruent, and we know that this side is congruent because it was congruent on the other two triangles. Okay, so we've got side angle, but we don't have a triangle congruency that we know. So we have to take a step back here, and we have to talk about the fact that these are right triangles. And that's kind of the beauty of this proof is, oh, we made those right triangles, right? They're still right triangles. What did we study the other day on Tuesday about right triangles? There's actually and I haven't shown y'all this, and I'm not going to. There is a conjecture somewhere that talks about right triangles and hypotenuse and one leg. So, and I don't care if you memorize that or whatever. So think about this. If you know, well, put a little thing in here. Let me, I'm going to, as close as possible, reconstruct this guy. This is just kind of small. We know that, we know that, we know this guy. Okay. If you have two triangles and two right triangles, and you know that they have a hypotenuse the same, this is the hypotenuse because it's across from the right angle on both of them, and they have a leg the same, then you actually do know that they are congruent. Now there's a whole entire thing about that, but let me show you why. Basically what you know is a squared plus b squared equals c squared, right? On both of these. So let me say the other one's a1 plus b1 equals c1, all of those squared. Okay.
There's only one thing that
Say it again.
there's only one amount that they're doing, like,
There's only one number that the other side can be. You agree? If this is A and this is A1, this is C. C is actually the same number. It's not a C1 and a C. And then if this is B and this is B1, actually says no matter what it is, if they're the same, so let's say, and I'm going to pick nice numbers for us, but then there's a whole proof for this. But let's say that this was 3. The A is a 3. We have 3 squared. And over here, same thing's going on. Okay, 3 squared plus something squared. And we know that the 3, 4, 5, I'm picking 3, 4, 5 because it's nice. The C would have to be the 5 squared, and it would be 5 squared on both sides, right? What does this guy have to be in the middle? 4. And it has to be on both of them. And that's what it actually said. Oh, well, once you get there, this guy has to be the same number on both of the Pythagorean theorems that we worked with the other day. Okay, so it doesn't matter. And these are specific numbers, but there is an entire proof that shows that for generic stuff. I don't care about it. I don't care enough to do that. But what we do know is, hey, look, we know we can figure out that these sides have to be the same. So now what do we have? Side. That makes sense. And that's why they don't really prove the third side. Like for this particular setup, they call it the hypotenuse side conjecture, I think is what it's called for right triangles. So anyway, we end up with this guy right here. I'm going to give him a double heartbeat congruent to this guy right here. Okay, why do I care about that for my overall picture back here? This triangle is congruent to this triangle.
Because that shows all three of the
Okay, we have all three of these perpendiculars congruent to each other. If these two triangles are congruent, then all of their parts are congruent, right? All their corresponding parts. So that tells me what's going on up here at angle A.
Thing was bisected.
That has to be the same angle, right? Okay, so we had to have bisected that angle. So 1, 2, 3. I don't know what I'm up to. I think 3. Yeah, yeah. There we go. So since these two triangles right here are congruent, then their angles up here have to be congruent also. Corresponding parts of congruent triangles are congruent, right? So that tells me that we had to have bisected this. So this segment, which we already know is concurrent with the other two, right? Because that's how we constructed it, has to be the angle bisector. There you go. So now we know all three angle bisectors are indeed meeting at the same point. So the first two you can just assume, because we know two line segments will meet in one point. But the third one you have to prove. Isn't that fun? Ooh. Goodness. So now that's number 7 in your proof project. So you can do that. Add it to your collection. I don't know how many of them we've done now. Probably about 4. 3 or 4, I think. All right. Now, on your test, am I going to give you one that's that in depth for a proof? No, I'm not going to give you one like that for a proof on the test. I'm going to, because that one took us like 20 minutes-ish to do, right? So I'm going to give you one that hopefully, bless you, hopefully you can finish in 5 or 10 minutes, right? Because I don't want you spending 20 minutes on one problem on a test. That's just crazy. And they're not going to be worth that many points to be doing that. So, yay. All right. So make sure that as we get close to test 2, that you're looking at those sample problems that are online and that you will be able to do some proofs. So the proofs are due next Thursday. Next Thursday, we're going to meet. And next Thursday, we're going to go over sample problems review for the test, right? Yes.
I don't know if it's something that we already answered. Are proofs part of the content exam?
They don't do it like that. So on the content test, what they do is they'll start a proof for you maybe, and they'll say, what's the next logical step in this proof? So they don't expect you to do all of it, but yeah. So for instance, if you got here and you saw the angle side thing, then you would say, oh, well, and I had drawn this little kite-ish looking thing for you. You would say, well, the next logical step is that I have triangle congruency for angle side. And there'll be 4 different choices. It's all multiple choice. And it'll be like, there's always one answer that doesn't make any sense at all. Like it's the dumb question, the dumb answer. Okay, and then there's always one distractor answer. So like if we use angle side here, maybe it might say, oh, angle side angle might be your distractor answer. So you'd have to make sure of what order you had them in. Okay, and that's actually something I was going to say earlier. And then there will be the right choice. All right, so distractor answers, watch out for this. What I was going to say earlier was, if you wanted to here, if you didn't come up with angle side, you could have looked here and said, I know that, let me zoom that again. Sorry. Hope you're not getting seasick in Zoomville. Okay. You could have said, look, I got angle, which forces the third angle. Does that make sense? Like we know that these two angles up here are also congruent because I've got angle, the third one has to be because they have to add up to 180. And so then you could use some other something, like you could have used angle side angle if you put into your proof, oh, so I know all three angles, so now angle side angle. So you could come up with a different thing, but on the content test, that wouldn't be the natural next step if I had just given you this. You might say, oh, I can find the third angle. That'd be all right. The third angle is congruent. Okay.
The entire content exam is multiple choice.
Yeah, but the problem is that they do that kind of thing to you. There will be distractor answers on there that you're like, oh, that looks really good. It looks like that could be it. It's kind of like on the PPR test, well, where they'll say, what's the best choice for you to make? Okay, what's the best next step for this proof? And so there'll be maybe 2 or 3 things that you would eventually do. Like I might eventually use corresponding parts of congruent triangles or congruent, but that's not the next step. You know what I'm saying? So you have to kind of really pay attention to that kind of stuff. So they do that to you on the content test. All right. Okay. All right. Looking at the test and all that good stuff. Looking forward to the test. Oh, almost finished with this semester. That means I have a lot of grading to do. Crazy. I'm working on it. I'm working on it. Okay. So I was going to. Hey. I was going to show you some 3-dimensional stuff. So the next 2 sections of material are all about 3D objects. So we've run out of, we're not going to do anything more with pentagons or hexagons or anything like that. Like the big content for this class and what you would see on the state board is the triangles and quadrilaterals. That's the big stuff, circles. Okay, stuff beyond that, they kind of want you to know some of the general rules, like, okay, if I'm using a pentagon, then I know how to find the interior angles of a pentagon. It's that 180 times n minus 2 formula that we've seen before. I know what regular pentagons look like, that kind of stuff, but nothing really specific about properties of pentagons and things like that. So your videos that you're watching for Tuesday, because we're not coming to class on Tuesday, we're not Zooming on Tuesday, I will actually use these type of objects with you that are the 3-dimensional. What's this one called? 3-dimensional cylinder, right? It's got circles for the bases, and then it's just got one lateral face here, right, all the way around. So I bring out the nets. Okay, so there's a whole entire conversation that you're going to do about surface area and volume and all that, and those are on the videos. Okay, so I'm not going to redo all of that, but this is a net. So if you see it, if you saw it in the thing, it fits into the cylinder, right? Or if we make our own, sometimes it fits around the cylinder, okay? But the idea is that this will approximate for me as well as I can get the surface area, and surface area is what? For any object, this is a cylinder, but it doesn't matter. Surface area is what? Yeah, it's like the total area around. So think about it. I always think if I was wrapping this, if this was a Christmas present and I was wrapping this thing up, then what would it take to go all the way around the surface? That's what we mean. So that's what this net is doing for me. It's kind of giving me the surface area. And you can see what happens is, actually for cylinders, what they do is they use really small rectangles. And the idea being, it's a calculus concept. If I made them infinitely small as I could possibly make them, then I could have an infinite number of rectangles and eventually they'd be like a line. That's how skinny they'd be, right? So I can have this, but when I see this piece, this was the round surface, right? It's one long rectangle. Y'all see that? Because I just piece all the little bitty rectangles together. So if I was drawing this net, I'd have to do something with a circle and then a really long rectangle and then a circle, right? And the question becomes, is that the only way I can do it? Like, do the two circles have to be right here in the middle? No. Okay. I need the two circles, right? Because they cover the bases of the cylinder. Okay, I need them for that. But they don't have to be right here in the center. For instance, I could have put them down here on the end, or I could have put one on one end and one on the other end. So what we're going to look at right now is, first of all, making our own nets and what that would look like with students. Like, do they have to make the same net that we have and that kind of thing? Okay, so here's another one. You can tell me about him. What's his base? Hexagon. Notice I moved it until it was in the alignment that I wanted it to be. Like, that doesn't work for me. Oh, cool. That's a trapezoid. That's a hexagon. Okay, so this has bases that are hexagons, and then it's got these faces, right? How many faces do you think there are? 6, right? Because there's 6 sides here on my hexagon. So there's going to be 6 faces. And what does each of those faces look like? Rectangle. That's because this guy, bonus question, is this guy a pyramid or is he a prism? Prism. Pyramids are what? Yeah, one base, and so the faces come up and meet at the top, right? Like this. This is a pyramid, right? So only one base and all the faces come up and meet at a vertex, basically. Okay. So this is kind of the normal pyramid we're used to seeing. But the hexagonal pyramid, which, by the way, if you get one of these sets, they're really well designed, because look at how the hexagons are actually the same size. So the bases are actually the same size. So these have the same base, whether they look like it or not. They line up exactly. And then you can see, oh, it still has 6 faces coming up, but they're slanted. They're not straight up and down. They're not vertical. Okay, so that's the difference between a pyramid and a prism. But we're just dealing with prisms today. All right, you'll have more on pyramids later. Okay, so again, here I go. I've got the 6 rectangles. We can see them. I've got the 2 bases. They're hexagons. I can see them. And again, those hexagons don't have to be in the middle. It's just that this company, whenever they make them, they put their bases in the middle and then they build the rest around it, basically. So that's what that looks like. Okay. We're going to do an easier one. So I want you to know these are out there. You'll see them in the videos and stuff, but we're going to do an easier one. What I want to do is I want to talk about drawings. Yay. And there's basically 3 different things that you might see as you're working on geometry with your students, that kind of stuff. So you're going to see the nets. You're going to see isometric drawings. And you're going to see orthographic drawings. Okay. So the nets are pretty easy, and I brought some, I put this on D2L if you guys want to see it. But I brought some centimeter paper. With. And if y'all want extras of this, I have a whole entire palette. Oops, sorry. You got the streamies in there. Okay. So if you're in D2L, I did upload this. So this is just centimeter grid paper. Okay. If it's copied appropriately, what it tells me is that each side is 1 centimeter. Each side of a square is 1 centimeter. So this should be 1 centimeter squared, 1 centimeter squared, 1 centimeter squared. So what I want to do is we're going to do a pretty easy one. This one is, let's see if we can get it. Is it a prism or a pyramid?
Prism, rectangle.
Prism, and I'm hearing it's rectangular. Okay, it's a rectangular prism. Now, this one actually technically has a square on the bottom for the bottom, but it doesn't have to. Like your rectangle can be oblong and stuff like this. This one just happens to have a square. All right, so what I want to do is I want to use our centimeter paper to give ourselves a picture of what a net would look like. Okay, now you can't do this one. So here's the one that the company gave us. You're doing a rectangular prism. If you want to, you can, if you were doing this with kids, you could assign numbers. So you could say stuff like, well, let's assume that this is 4 across, 8 down, whatever. So you can give numbers. And then whenever you got your students' pictures, they would all look fairly similar. That would help us. So I'd like to do something like that. Let's assume. What do y'all want to assume? I don't care. I'm going to use 4, 4, and 8 if nobody else. 4, 4, and 8. Okay, let's do 4, 4, and 8. So what that means for me is this one from the company has a 4 by 4 square on both ends of the second rectangle. And each of these rectangles is what? 8 tall, 4 wide. Everybody agree? Okay. So first up is nets. Have your students draw a net for this thing. And I don't want you to draw this net. Draw a different net.
So not the 8 by 8, 4 by 4.
Not this exact picture. So I want you doing 4 by 4 and 8. My dimensions 4 by 4 and 8. But I don't want this picture. So it can't be rectangle, square, rectangle, square, rectangle, rectangle. That makes sense? It would help if I could count. Of course, if you gave them smaller dimensions, it wouldn't use as much paper, so you could get more pictures on one piece of paper with your kids. Okay, is my net complete yet?
No.
Why not?
It's missing another base.
It's missing another base. So I have, for instance, my top base here, but I don't have the bottom base. Okay, so the question becomes, does it have to be right here? No. it can be attached to any of these rectangles I want. So I'm going to put mine, just to be difficult, over there. Okay, so I've got one base over here and I've got one base over there. Okay. So how do I, as a teacher, if you guys are in my middle school classroom, how do I confirm that your stuff is going to work?
You cut it out and build it.
Mm-hmm. Exactly. And that's, we actually normally, if I was teaching like a 1350 or 1351 class, I would make you do that, and then we could put them on the stick and paste them on the walls or something like that, so that everybody could see. Okay. So what we would want is when you cut this figure out, and of course you don't cut down the middle here. It should all be one big net, that one big continuous piece here. When I cut this out, I would fold it on these interior lines. Those are my fold lines, basically. And hopefully, when I finished, I would have this space would be over here and this space would be over here. But when I fold this in, what happens to the base that's way over here? It's connected here, right? So as I come in and I come in and I come in, it's connected right there. It would be up here instead of down there, and then I just fold it down. Okay, so does it make the three-dimensional object I'm after? That's the question. And the answer is yes. So ultimately, if you had lots of time and you didn't have COVID going on and that kind of thing, you could have students cut those out. And then once they folded it up like this, you just give them a little piece of tape, tape, and then they also have a rectangular prism, right? And by letting them kind of pick where they're going to put stuff, it lets us know, lets them know if their thing is going to work okay. Now, what we don't want is we don't want the base connected just barely on the corner here, right? So we don't want the base kind of hanging out here. It needs to be connected on a side so that it'll, when it folds up, it's obvious where it needs to go to fold in. Okay. So those are nets. And I think somebody's doing nets for their presentation. So hopefully we have some really cool examples and stuff you could do with your students. Okay. Again, you can scale these down, scale these up, however you want to do it. I'd like to give everybody the same measurements for me personally with my class. That way, when I see all of your papers, I can just go, yep. If one's really huge and one's tiny, then you have to, like, as a teacher, just a teacher moment, then you have to really kind of look at it and go, okay, does that scale properly? Like, if I had done this 2 by 2 here, that'd be fine, right? I just wasn't counting when I did that. But if I'd done 2 by 2, it'd be fine. But then this guy right here, this rectangle, would need to be 2 by 4 instead of 4 by 8, right? To scale it down the way it needs to be. And that's a dilation. So that's not a rigid state transformation, because we dilate it, we make it smaller, we expand it, we make it bigger. Okay. So those are nets. Now, second, isometric. What the heck? Isometric.
Like something by itself, ISO.
Something by itself. Kind of. So basically, isometric, what we mean by that is that we draw things and they're not necessarily exactly to scale. Sometimes you have to fudge it to make it look more realistic. So this would be, and I'm really terrible at this, guys, I apologize in advance. This would be when you, the teacher, draw it as if it was a three-dimensional object. Okay, so let's do the same guy.
Like when you draw a cube.
Yes, like when you draw a cube and it's supposed to look three-dimensional, and mine always sink, because what happens is whenever I go to do it, for instance, I wouldn't go all the way across 4 whole cubes, 4 whole squares to make the top of that cube, right? I have to fudge it a little bit to make it look more appropriate. So what I would normally do on this one is I would do the rectangle first, the rectangle piece, because he's the biggest portion, and I can do him kind of vertically. I'm going to do him on the same page. 1, 2, 3, 4, 5, 6, 7, 8. Okay, by 4. And I'm terrible at these. I'm just telling you, absolutely. Okay, So then what? To make this guy look three-dimensional. First of all, somebody might have canted this just a little bit that direction so it wasn't straight up and down. But I'm terrible at it, so I never do that.
Side, move up at least one row and over at least one.
Okay, up at least one row and over at least one row. What does that do for me?
That gives you either your back side or your front side, whichever, however you draw yours.
I'm gonna do about like that, I think. So for me, it's kind of across two diagonals of squares. And she's saying it gives me one of the other sides. Are you talking about the base here, or are you talking about one of the vertical faces here? Okay, one of the vertical faces. That's okay. No, I just want to make sure I'm drawing what you want me to draw here. So when I do that on the top, and then what I would do is go ahead and do that on the bottom and try to make sure it matches as well so that we can see this face coming out here. Now look. This one was 4 across, and this one's only 2 diagonals across. Now, a diagonal is longer than just the side of this square, right? We know that because when we look at this, this is a right triangle, right? And this is 1, and this is 1, then this guy over here is square root of 2, right? So the hypotenuse, so to speak. So this guy is bigger than 1 unit, is what I'm telling you. So this is actually, even though I did 2 diagonals, it's bigger than 2 units. And so visually it looks-ish about the same. And we know we're trying to make it three-dimensional, so we're giving it that depth, right? Okay, so that's what happens. All right, then what?
Do the same thing
To the top, up here, over here. Okay. So we want to match the slant, basically, the slope here. Because we're trying to create the square that's the top base, right? That's what I heard. And then here. Okay. So when I was growing up, they made us also do the back side, okay? And depending on the book or whatever you're doing, they will also show that, but normally they do it kind of as a dashed thing. Where the dashes like that make you know, oh, this is the back side of this thing. And you can't really see it, but we know that it fills in that direction. And so when I was growing up, we always had to finish that out. Now, a lot of books nowadays don't show that back piece like that. Okay, they would just stop. No problem, Mary. She had to do. All right. So that's a pretty decent drawing, and it works out really nice because I have the grid paper, so it makes it better. When I hand draw these without the grid paper, it's way worse. I brought in also, and I just want to show these, and if you're in commerce and you want one, you're welcome to grab one because I have plenty of them. They have these awesome little Post-it notes. It took me a while to find them. Never had them when I was, stick them up there. I never had them whenever I was teaching high school geometry, okay? But so these are Post-its. So I can literally just slide this off, if I can get one of them, and stick it somewhere. Like if this was my worksheet that I wanted to give you guys, it just sticks onto it. It's a Post-it note. And they have different shapes. Okay. Here's the cone. And this is the one, there are 2 that we use the most in the math department, I've noticed. This is the dot paper. This is really tiny, but these are supposed to be evenly spaced across, so it's nice for doing things like what we just did. Because you have dots to connect, basically, without having to have grid paper. So those we use a lot of. see that? That's cool. Okay, and then they make one, and I didn't bring one with me, I don't think. Here's a cube. They make one that is the coordinate system plane. And I actually use that one a lot whenever I was making college algebra exams because I want to graph something. And I just take that sticky and slap it on my test paper, and then I can make whatever graph I wanted. Sometimes importing graphs into a document, a doc, is very difficult. So if you are looking for something that will help you out, these sometimes help, okay? The diagrams of the picture or of the shapes, those are a little bit difficult for me because they are, they're big. So like if I was trying to put this on a test, it would take up so much space, right? So I would normally like shrink it down, but it's kind of nice to just have a pre-made thing of that too. So anyway, I brought those if anybody wants some dot paper. Dot Post-it notes. You're welcome to them. All right, so this is isometric. And by the way, imagine how complicated this becomes if we want to do, say, a hexagonal pyramid or prism. Then I have to figure out how to make my hexagon up here and how to make it look proportionately correct whenever we know this wasn't 4 across, right? So have to watch out for that. Okay, that's isometric. And then the last one is orthographic. Got that one. Where did it go? Here it is, orthographic. So the orthographic is a weird one because they actually use it, and I'm going to do one with this, and then I'll show you an example out of the book. They actually use it for being able to reconstruct a shape, basically. So what they do is they do the front view, the top view, and one side view. Okay. So if I had this object, let me put it back together for us. If I had this object, say this is my front, then what would that look like whenever I made it? Just a rectangle, right? Okay, that's not bad. I'm going to shrink mine by half because I'm out of space. So my front would be a 2 by 4. If you've got space, it's a 4 by 8, right? That's not bad. Front's okay on this one. Okay, and they literally label them just like this. The front looks like this. The top looks like head on. Okay, nothing else, just straight on. What does that look like? A square. Okay, and again, if you're doing the regular size like this, it would be a 4 by 4. I'm going to do a half size, so 2 by 2. And then the right side. Now, this one's kind of a boring one because it's just one prism, so it's not that big of a deal. But normally you would say, if this is my front, then what does the right parts look like? Now, the right side of this one's boring because what? Here was the front, here's the right side. Doesn't matter, right? They're the same. So my right side here is actually the same as my front view. And that kind of, the fact that my right side is the same as the front side, when I go to reconstruct this, if you gave me these 3 pictures, I should be able to reconstruct it and say, oh, this looks like this. Your original 3-dimensional object looked like this. Okay, that's the idea of giving me all 3 of those pieces. I don't really need the left side. Why don't I need the left side?
Just like the right.
Because it's a profile, right? So if this is the profile of this thing, then the left side looks the same as the right side. Exactly, it looks just the same. Okay, and if the top looks like this, then the bottom looks like this, right? So I only need 3 pieces. So this is the orthographic. And again, I'm not doing anything with an orthographic most of the time, unless I have some kind of grid paper or dot paper so I can make it work out. Okay. All right. Is everybody okay with that? Orthographic looks like. So let me give you a more complicated version because that one's boring. clearly, that's not a big deal. What if they gave us this this isometric picture? So this is isometric. How do I know it's isometric? It looks like a 3D drawing, right? Okay, what we would normally think is a 3D drawing. So that's the isometric, okay? So that's what we would be used to. You can tell it has depth and stuff that my rectangular prism didn't have, right? So that's different. The question is, what does this look like from the top? So kind of looks like a rectangle, because why, Summer?
Because you're not going to be able to see the different layers. You're just going to be seeing the 2 by 3, 4.
Good. Okay, this looks to me, and I'm with you, if this is 2 across, okay, assume this is 2 units across on the top, then all the way across here is what? Maybe 4 units, it looks like. So in general, I count the dots. If it's got on dot paper, if it was on grid paper, I would count the grids. So I would say 1, 2, 3, 4 all the way across. So it doesn't matter that this piece up here is shrunken in from the rest of it. If I was looking straight down, straight head on at it, this would be 4 across. Everybody agree? And then what about, so I'm still looking straight down at it. What about the height of it, so to speak? Looks like 6. 1, 2, 3, 4, 5, 6. Is everybody okay with that? So the top view would just be a rectangle, and it's like a 4 by 6. Okay. But we're going to do a little something with that. So let me, anybody need more paper? Where's my paper? I need more paper. You don't need more paper? Okay, she's good. I have completely filled up my paper. Sorry guys in Zoomville. Hopefully, oh man, you're just getting drilled. First, you got a stringy thing.
You're doing it on purpose.
On purpose, I'm picking on Maria today. All right. So we want to make a 4 by 6 rectangle is what we're saying. Oh, too far. Top view, that's what we're going to do first. Okay. There we go. Okay. 2, 3, 4, 5, 6. Okay. Now, what they're going to do on this is a lot of times they will just say, okay, this is a rectangle, we know that, but then they'll come back and they'll kind of do interior lines, if that makes sense. So this very top piece we said was a, looks like 2 by 2 square and then cubed all the way around, right? So they'll kind of go, okay, this is what it looks like. There's one layer that's like that. The next piece looked like it came out all the way to the edge, right? And yeah, 4 by 4, I like it. So it came all the way to the edge, but it was a little bit taller or deeper, or however you want to think about it, than the top piece. And then the bottom is solid all the way across. It's completely 4 by 6 on it. Okay. They don't always put these little things in there, but if they do, that helps me to form the different layers, which is nice. Okay. That's the top. Head on look at it. Okay. What about the front? Here's my picture. Now, and they've got it marked for me, thankfully. They said, here, let this be your front.
It's going to be a 4 by 4 with a 2 by 2 on the left side.
Okay, 4 across, I got that. And she wants to say 4 tall. So let's count how tall it is. This bottom layer is 2 tall. So it's like I'm looking straight at it. And then the next layer is how tall? 2 tall, so that's 4 total, right? And then how about this top one? also too tall. So how tall is it?
6.
6 tall, and across I heard 4 wide. Is that right? Okay, so 6 tall and 4 wide. That sounds a lot like what we just did. So how am I going to, and she mentioned this, Maria mentioned this, how am I going to distinguish for anybody out there how they would look, how it would look different to them? Oh, I know what we did wrong. It doesn't go all the way over on the top, Ashley says, right? I went 6 tall, which I should have, but I don't go 6 tall over here, and that's probably what Maria was trying to tell me. It's only 4 tall on this piece over here, right? So looking straight at it from the front, the left side of it will be 6 tall, but the right side's only 4 tall. So it doesn't need to be a rectangle, right? It needs this piece cut out of it. Sorry about that. I can't erase. So instead of looking exactly like a rectangle, it looks more like what? Yeah, more like an L or a stair step or something like that. Okay, and again, if I wanted to give that little helping hand, I would put in the layers. And so I would say, okay, this one is too tall and this one is too tall. 2 units tall, right? So that kind of tells people, oh, there's a cube on the top that doesn't go all the way the width of the entire piece. That makes sense? All right. All right, and then last but not least is the right-hand side. Okay, and again, they pointed it out for me. The right-hand side is this face over here, and they actually shaded this one for me a little bit so I can see it. So what is this? Okay, 6 deep.
4 high. Or 6 high on that side.
Ah, it depends, right?
Mm-hmm.
On this left-hand side, it's only 2 high, but right in here, it's 4 high, and right in here, it's 6 high. So this looks like what? Stair steps, right? Okay, it's 2 up and then over and then 2 up and then over and 2 up. So it's 6 across and 6 tall, but it's not all the same height. So you have to be careful about it. So let me get that in there. Right side. So I need 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And for me, I mean, y'all might be better at this than I am because I stink at drawing anyway. And some people are really good at seeing like perspective and visual and angles and stuff like that. But I really kind of stink at it. So to me, I would kind of get the overall, okay, it's 6 by 6, but only 6 on the bottom. Then it goes up 2, over 2, up 2, over 2. I can't count. Up 2 and over 2. Yeah, there we go. So it does look kind of like a stair step on that. Okay. And again, if you wanted to, now this one, if I was going to draw the layers in there, what about here? The first layer and the second layer come all the way across, right? They would come all the way toward me on the edge. So the only kind of defining line there would be what? The cube on top. Yeah, he's at a different depth to me than what the other 2 layers are. So I feel like if you think about it as layers, if you think about it like whatever, depths and heights and stuff like that, it helps. And if I had all 3 of these pictures, then hopefully we could reconstruct this and we would say, okay, this is solid all the way across, right? This is solid all the way across on this second layer, but it doesn't come all the way to me whenever I'm looking at it face to face, right? Like straight on the front, it doesn't come all the way to me. And this is just one little cube on top. So hopefully using the 3 different pictures, I would be able to say, okay, we reconstructed this using centimeter cubes or what do they call those? Snap cubes or unit cubes, Unifix, that's what they call them, the Unifix cubes that snap together. Have y'all seen those? Yeah. So I could reconstruct this whole picture, and then I could just have it in front of me and say, okay, when I look at it, is at the front, is this what I see? When I look at it from the top, is this what I see? And make sure that your blueprint, so to speak, actually matches what your physical reconstruction looks like. Oh my goodness, so you can see these can be quite the pain in the rear, right? I don't do tons and tons of drawing because I'm just not an artist. 3-dimensional is really difficult, for me at least. So I try to keep it simple. I try to make sure I have grid lines or dot paper if I need to do that. Okay. There's no homework on this section. Of course, we're just working on projects for next week. Y'all remember that your write-up for your semester-long project is due on Tuesday, and you'll just load it into D2L, okay? And then the presentations are due on Friday, but hopefully you don't wait until Friday night to try to post them, right? And what about Tuesday? Write-ups are due and no class, right? Don't come to class, don't come to Zoomville, all right? All right, so watch those videos on Tuesday since you're not coming to see me. Let me call roll real fast.
Do you have anything
And
to do tonight?
I'm gonna stop the video. Is there anything due tonight? I don't think so, right? 7-1 was like your last homework, and that was due Tuesday. Yeah. I'm gonna stop the video. Bye, people on video.